All right, moving on from that. Um, so the question arises now, why does hydrogen only tend to bond to one other hydrogen? Why does hydrogen only want to share so it has a total of two electrons? Why doesn't hydrogen pair up with three other hydrogens? So then there's four electrons total, and instead of H2 in nature, we'd see H4. Well, this has to do with the octet rule, which is just a set of loose rules that elements tend to follow these rules can help us predict how molecule structures are. So this rule was also discovered or introduced by Lewis. So the same guy as the Lewis structure, he comes up with the octet rule. And so this is Gilbert Newton Lewis. This guy, he never, so there's a lot of he discovered a lot of fundamental chemistry. He came up with a lot of different answers for things that we learn in Gen Chem. He never won a Nobel Prize, and I think he was very salty about this. And I think so. He died in lab in his own research lab. He passed away, and his death is very controversial. So some people think he just died of like heart related things, or this or that. But I think there's a theory going around that he might have committed suicide by cyanide poisoning, maybe perhaps because he did not win a Nobel Prize, but we'll never know. So anyway, that's Gilbert Newton Lewis. Um, so he comes up with the octet rule. So this is a rule that governs a lot of what we see when it comes to bonding. So the octet rule says that atoms tend to lose or gain or share electrons to achieve a noble gas configuration. So noble gas configuration either means valence electrons, or um, two valence electrons for hydrogen and helium. So where these octet and where the number eight comes from is because there are two electrons in an s orbital, and then there are six electrons in a p orbital of the same principal in the same level. So that's where eight comes from. And that's how you fill up an entire valence shell to get to a noble gas configuration. So once you have all of um, the s and p orbitals filled, now you've achieved a noble gas configuration. And then so it's octet 8 valence electrons for most elements, but then for hydrogen and helium, because in the 1s sorry in the n equals 1 shell, you only have an s orbital. There is no such thing as a 1p. There's no such thing as a 1p6 orbital. That doesn't exist. All right, and so because the first noble gas configuration, helium, only has two electrons in its valence shell, that's why for hydrogen and helium, two electrons are preferred there. All right, so that's what the octet rule means. So, but for like 95% of the other elements, eight valence electrons are what we're going to try to achieve. So either atoms tend to lose or gain electrons. So this would be indication that there's a transfer happening. So this would be for ionic compounds, or there's sharing electrons. So this would be for covalent bonding or covalent compounds, whatever. All right. So some examples. So here I have some examples. So we have diatomic bromine, so Br2. So if we take a just neutral bromine atom, so this is just bromine. What is bromine? 35. So bromine 35. If you look at it on the periodic table, it's a halogen, so there's 7 valence electrons. So you can count here that there are 7 electrons. So since this is diatomic bromine, we're bringing two bromines together. And so you see that there's this vacancy on one of the bromines there's a vacancy. There's seven electrons around valence electrons around bromine. It wants eight, and then the other bromine that you bring in, there's also a single vacancy that it has seven electrons, but it wants eight. So what happens is that in order the most efficient way to give each atom eight electrons would be to share these two electrons to form a bond. So we're not going to transfer an electron because if we transferred an electron, then we would leave this bromine with six electrons and then the other bromine with eight electrons. So we don't want to do that because we'd only be fulfilling the octet of one of the bromines. We want to fulfill the octet for both. So what we're going to do is share those electrons. So then what you'll get is you'll get a bond, a electron pair. So you can kind of think, okay, there's two electrons in that bond. So when you look at the octet around one of the bromines, so let's just look at one, we're going to include everything, all the electrons around bromine, including the bond, both electrons in the bond. So this bromine has eight electrons. Its valence shell, its octet is complete. While the other bromine, if we count the electrons around it, there's six around it. And then if we again also include the bond, the one electron that it's sharing with the other bromine, this bromine also has eight electrons. So this would be a covalent compound or bond because electrons are being shared. Excuse me. All right. And so here is another example between a hydrogen atom and a chlorine atom. So hydrogen is just 1s1, while chlorine is it's argon 4s2, 2, 3, 4, no, 3s2. Oh no, wait, nope, neon. It's neon. 3s2, 3p5. So you can see here, the n equals 3 is the outermost shell. There are seven total valence electrons. You see that there's seven electrons around the chlorine's Lewis structure. There is one electron vacancy, but hey, look, this hydrogen we can share an electron with hydrogen and fill that vacancy. So this is an example where it doesn't have to be the same atom. Like we had bromine and bromine with the other example. We had two hydrogens sharing electrons. We can share electrons with other elements as well. So this hydrogen is going to share its electron with this chlorine. All right, and so then you'll get this bond, this figure here, where there's two electrons in that bond. So again, you can kind of check out the octet rule for both. So for hydrogen, these are all the electrons involved with hydrogen. So all the electrons involved are the electrons around the atom itself and all the electrons involved in the bonds, in any bonds around that hydrogen. So here there are two electrons, and so that's good because hydrogen's one of those exceptions where it doesn't fulfill eight electrons, it only wants a total of two. And then if we look at chlorine, so look at the, so maybe I'll just define this. So octet will be the electrons around the atom in question. And how do I want to say this? All electrons involved in bonds to that atom. So that means one bond equals two electrons. I just want you to know that I don't want you to like, oops, draw your box around this chlorine and I don't want you to do that. I don't want you to split the bond in half, right? Because then you would just count seven. Chlorine has seven electrons around it. You don't want to do that. You want to show that because you're sharing an electron with hydrogen, now chlorine has eight electrons and its octet is fulfilled. All right. Okay. So I think okay. And then so let me just define a couple more things, but you know this now that the bonds are represented or the line between the atoms are two electrons being shared by two atoms. So 2 electrons being shared by 2 atoms. Great. And then anything that isn't aligned when there's dots around the atom, those are unshared electron pairs. And those are shown as dots. Sometimes I might call them unshared electron pairs. I might call them non-bonding pairs. I call them non-bonding because they don't participate in bonding because they're already paired. Non-bonding, or sometimes I might call them lone pairs. So all these things kind of mean the same thing. So unshared electron pairs, non-bonding electrons, or lone pairs, they kind of all mean the same thing. And those are the ones that are indicated by dots. Okay, so let's go through some examples of fulfilling octets with different different elements and how we would go about that. So here's how I would approach a question like this. So we have an element oxygen. You might be asked a question, I have oxygen and hydrogen. Um, what draw the Lewis structure of the most preferred molecule containing oxygen and hydrogen? Right. So how would I would approach this is I would look at oxygen. I would probably first write out its full electron configuration. Well, I'll cheat. I'll do the noble gas configuration. So it's a helium because I don't care about helium, or I don't care about the inner shell. So it's helium 2s2 2p4. All right. And so if you look at this, there are 6 valence electrons. So that means we want 2 electrons. We want 2 electrons to fulfill octet. All right, so if we, what did I want to say there? So that means that oxygen, so it wants 2 electrons to fill its octet. Essentially, this means that oxygen will make 2 covalent bonds to fulfill octet. Octet. All right, so whatever valence electron deficiency you have will be made up by the number of covalent bonds that you'll make. So oxygen wants 2 covalent bonds because it needs 2 electrons to fill its octet. So we can kind of see that in action here. So if I draw, maybe a different color, if I draw the Lewis structure of oxygen. So again, look at the, we want to follow Hund's rule, look at the electron configuration. So there's 2 electrons in its S shell. And then we will fill P singly and then pair up 1P. So essentially, it looks like this. 1, 2, 3, 4. So this box is represented there. So there's 2 unpaired electrons on an oxygen. So these 2 spaces with unpaired electrons, ooh, those are great places to put some covalent bonds to share electrons with other things. So why don't we just throw some hydrogens around? So a hydrogen atom has one unpaired electron and another unpaired electron. So essentially what's going to happen is that this oxygen is going to share an electron with one other hydrogen to make one covalent bond there. And then its other unpaired electron will go here. All right. And so if you want to draw the whole Lewis structure, then it will look like this. And then there's 2 lone pairs right there on oxygen. So don't forget those lone pairs, the ones that aren't involved in bonding. All right, and so what is this? Ooh, this is water. This is H2O. Great. So again, we can kind of check our work and see, okay, what are the, do each of the atoms have their octets filled? Look at oxygen. Oh, remember that we have 2 electrons in each of these bonds. So if you count 1, 2, 3, 4, 5, 6, 7, 8, 8, oxygen's fine. And then if we look at hydrogen, again, remember, so for oxygen, I counted all of the electrons around, so all of the lone pairs around the atom, and then all of the electrons involved in bonding. That's what gave me 8 electrons around oxygen. So same thing for hydrogen. There are no lone pairs around hydrogen, so that's 0, but all the electrons involved in bonding, there's 2 electrons involved in bonding with hydrogen. So hydrogen has its 2 octet complete. All right. Okay, so let's do another example, phosphorus. So let's write out the electron configuration for phosphorus again. So, because that's always the best place to start. So neon, 3s2, 3p3. All right, so I see that there's 5 valence electrons. So that means phosphorus wants 3 electrons to fulfill its octet. So that overall means that phosphorus will make 3 covalent bonds to fulfill octet. Once you do a couple of these examples, I think then you'll just be able to do everything in your head. You won't even have to write out the electron configuration. You can kind of just look at the periodic table and be like, oh, look, nitrogen is, group 5. It needs 3 electrons to be to fulfill its octet, so it wants 3 bonds. So you might end up doing it in your head, but I would just want to show all the work here so you see it all in front of yourself. So all right, so let's do the same thing. So let's say phosphorus, let's write out its Lewis structure. So again, we want to reflect the electron pairing here. So 2 electrons in its S shell, and then there's 3 electrons in its P shell, but they're all going to go in singly because of Hund's rule. So 1, 2, 3. Oh man, look at that. There's 3 nice spots to just make some covalent bonds. Isn't that so interesting how that happens? So you can just imagine if we added 3 hydrogens to 1 phosphorus, and remember, hydrogen has one electron, that each of those spots, those lone electrons, will pair up with another hydrogen. So I'm just going to skip some work. So you'll see a molecule structure like this. Oh, that's not very good. Something like that, where there are 2 electrons understood in each of those bonds, right? So in each of these bonds, one of the electrons come from phosphorus, the other one comes from hydrogen. All right, and so this is pH3. All right, and so we can also look at the the octet rule. Does phosphorus obey the octet rule? So again, we want to look at all the lone pairs around phosphorus. So there's 2 electrons there, and then all of the electrons involved in bonding. So that's all of these electrons. So there's 2 plus 6, so that's 8. Yeah, so phosphorus is good to go. Okay, so here is another example, carbon. So all of organic chemistry revolves around bonds with carbon. So understanding the Lewis structure and the bonding description with carbon, very, very important. But the great thing about organic chemistry when you get there is that with carbon, it's very predictable. It's very easy to predict how carbon will behave because carbon almost like 99.99% of the time obeys the octet rule. So you'll always be able to kind of predict what's going on. And then because with transition metals, it gets kind of hairy, and sometimes the octet rule isn't necessarily obeyed, and there's lots of exceptions. But with carbon, it's like set in stone, always 8, unwavering. All right, so octet rule with carbon. So again, 1, write out the Lewis structure, or sorry, write out the electron configuration. So for carbon, it's helium, 2s2, 2p2. All right, so right off the bat, you see that there's 4 valence electrons. So carbon wants 4 electrons. So carbon will probably make 4 covalent bonds because it wants 4 hydrogens, or sorry, 4 electrons, 4 covalent bonds. All right. So I think earlier in this video I talked about we wrote out the Lewis dot structure for carbon, and it was something like this. So to reflect, to reflect the electron configuration, you were to draw. Let me do a different color. Draw carbon to put 2 electrons in its s orbital, and then singly place those p electrons. So in organic chemistry, carbon undergoes something called hybridization. So this Lewis dot structure isn't actually correct. So for an idealized neutral carbon, this would be, excuse me, the Lewis dot structure. But in molecules, carbon undergoes hybridization? Because you see right here how it's drawn, like with that phosphorus example, all those single places where there's a single electron, those are great spots to make covalent bonds. So as written, this carbon only has two places to make bonds. But because of the octet rule, we can see that carbon actually wants to make four. So that's why this undergoes hybridization. And what this essentially does is makes um, all electrons equivalent. But we won't go into much detail right now about this. We'll talk about it a bit later. So essentially, the true Lewis dot structure for carbon when it's in different molecules is actually this. So it makes all the electrons equivalent. So it looks like this. So now you can see that there are four perfect spots to share an electron to form a covalent bond. So if we take this, I'll move stuff around. So if we take our hybridized, this is our hybridized carbon. So if we add four H's, right? So for different H's, we'll place an H on each of these locations where there's a lonely electron, and then we will get, whoops, something that looks like this, where each bond contains an electron, two electrons. One of the electrons came from hydrogen, the other one came from carbon. Each of the bonds has two electrons. So now we ask ourselves, does carbon obey the octet rule? Well, let's just count. It's octet to count up electrons for an octet, count the number of lone pairs. Does carbon have lone pairs? No, it doesn't. So that's 0. And then count all of the electrons involved in bonding around that atom. So if there's 4 bonds around carbon, we have to count all of those electrons. So yes, there is a total of 8 electrons. Carbon obeys the octet rule. So carbon, its ability to form 4 covalent bonds to either hydrogens or other carbons is essentially the basis of organic chemistry. So here's an example of a organic molecule. It is vitamin A. And so if you look at any carbon center and count the number of bonds around it, it will always be 4. So it will always be 4. So let's just choose one. So let's look at this carbon right here. Remember, carbon wants 4 extra electrons to fulfill its octet, so it wants to make 4 bonds. So if we count, there's 1, 2, 3, 4 bonds around carbon, its octet is satisfied. Great. But let's look at the carbon next. Let's not look at that one. Let's look at this carbon. So you might be looking at this and be like, oh wait, like what is this double line? What is this double line? Well, this is a double bond. And so in the next slide, I'll talk about double bonds, but so you can just essentially think of that double bond as worth 2 bonds. So if you count all of the bonds around this, my highlighted carbon right here, there's 1, 2, 3, 4. So there's 2 bonds coming from the double bond. So this carbon also has 4 bonds. It also obeys the octet rule. So you can look at some of these other carbons. So this carbon also has a double bond. So it's 1, 2, 3, 4. So any one of these, you'll see that carbon always has 4 bonds, 4 bonds to it. And this is a very good way for us to predict structure when it comes to organic chemistry. All right, so vitamin A has double bonds in it. And so this is a different way we can achieve an octet, is instead of like our bromine example, bromine had 7 electrons in it. One bromine atom has 7 electrons, so it only needs to share one electron. But let's say, we had an element that had a deficiency of 2 electrons. It needs to share 2 electrons. So you could either get 1 electron from 2 different atoms, or oxygen can share electrons with 2 electrons with share 2 electrons with 2 other electrons from 1 atom. Okay, so maybe that wasn't the best way to say that, but let's just go through this and maybe come up with an example. All right, so having multiple bonds is just another way to achieve an octet, and there's a couple of instances where double bonds are actually preferred over making single bonds. So let's just define a multiple bond. And fun fact, in graduate school I worked with substances that had multiple bonds. So let's just define this. So a multiple bond is a chemical bond where more than one electron pair is shared between two atoms. So that means one electron pair is equal to two electrons. So if we look at our vitamin A example, so if we look at one of the double bonds, erase. If we look at one of these double bonds, so this double bond right here, there are two electron pairs in half of the double bond and then two electrons in the other. So double bond, literally, it's like just two single bonds. So there's a total of four electrons involved in that bond. So you can just imagine if we had a triple bond that there would be six electrons involved in that entire triple bond. So again, an electron pair or one bond is equal to two electrons. So we've seen single bonds where there's one electron pair or two electrons total. Sometimes we talk about bond order. So if a substance only contains single bonds, we would consider that the bond order of that substance to be 1. So if we had a molecule like X bonded to another X where there's just a single bond, we would consider the XX bond, we would say the bond order equals 1 for that substance, for example. I'll just say example. All right, and so then simply for a double bond, you have two electron pairs. So that means there's 4 electrons involved total. Our bond order is 2. So if we had an example compound, Y, between Y, and there's a double bond between it, we would say that the bond order equals 2. And then finally, you can predict what a triple bond would be. You have 3 electron pairs, 6 electrons total involved, a bond order of 3. And so if you drew that as a molecule, you would have a Z triple bonded to a Z, and its total bond order here would be between the Z and Z atom is 3. So I told you that in my graduate work, I worked with substances that contained multiple bonds. So me personally, I worked with compounds that contained quadruple bonds. So quadruple 4, so that's actually 4 electron pairs and a total of 8 electrons involved in that bond between a molybdenum and molybdenum core, and then the bond order there between that compound was 4. So fun fact. And quintuple bonds also. So 5 bonds also exist. I believe it's between chromium atoms, right? All this weird stuff, it usually comes from transition metals. They're a lot more flexible. They can do a lot more stuff than these nonmetals can. And yeah, so I think chromium, I believe it's chromium, can do a quintuple bond. Okay. All right. So in general, the more shared pairs you have, or the higher the bond order, the stronger and shorter the bonds between the atoms become. So the trend here, as we go down, it gets shorter and stronger as we go from single, double to triple, and then to quadruple. All right. Okay, what's this examples? Okay, so let's look at some examples of molecules that have multiple bonds in them. So for example, we have CO2. So again, so let's remember our octet rules that we just kind of went over. We're kind of looking at all of the same, we're going through all of the same steps. I'm gonna probably skip some of them. So remember, the first thing we do is look at the electron configuration to determine the how many electrons are needed to fulfill an octet. You have to do that for all of the atoms that are in the compound. So we need to figure out, okay, how many electrons does carbon want and how many electrons does oxygen want, and then we'll divvy up all the electrons as fairly as possible. But first we need to take inventory of what everybody wants. So carbon, remember its electron configuration is helium, 2s2, 2p2. So it wants 4 electrons. Oxygen, it is helium, 2s2, 2p4. So oxygen wants or needs 2 electrons. All right. So we still need to obey the octet rule when we put things, when we put substance, when we put together our molecule. So how CO2 comes together, we put carbon in the center, we put oxygen here, because oxygen, so carbon wants 4 electrons. Oxygen needs 2. So if and we have 2 electrons, or sorry, 2 oxygens in CO2. There's 2 oxygens. So this oxygen wants 2, carbon wants 4, and this oxygen wants 2. It's just kind of like a puzzle now. We need to kind of put it together. Oh, wants 4. So I can just imagine, okay, carbon or oxygen can share some electrons, 2 of its electrons with carbon to get the 2 that it needs. And then this other oxygen can share with carbon, get the 2 it needs, and then total carbon gets 4 electrons. So what happens when we put this together is that we form a double bond between carbon and oxygen. All right. So now carbon has its octet filled. But remember, oxygen also has it has 6 electrons total, and it only shared 2 of them. So that's how that comes together. Maybe I should draw the Lewis structure for all of them. So maybe I'll just kind of rewind a little bit. So this is our hybridized carbon, right? So there's a carbon there. This oxygen has 2 electrons, this 4. So 1, 2, 3, 4. And then another oxygen, 1, 1, 2, 3, 4. Wait, yeah, so 6. Okay, so you can see now that, whoops, this oxygen has 2 vacancies. This oxygen also has 2 vacancies. This carbon has 4 vacancies. So what's going to happen is these 2 electrons will pair up with these 2, and these 2 electrons will pair up with these 2. So this is what's happening. I should have started with this. Sorry, I kind of went backwards, but you guys can deal with it. All right. And so now you see that everyone's octet is fulfilled and everyone's happy. So there are 2 double bonds here. So we can, do the whole, does everyone have its octet? Is everyone happy? So oxygen, again, you do the electrons, the lone pairs around the atom itself, and all of the electrons involved in bonding. So that means 4 electrons total with that double bond. So here you can see that oxygen has 8. It's good. And then this carbon, all lone pairs around carbon, there are none, but then all the electrons involved with bonding. So that's all of these bonding electrons. So all 4 electrons, or sorry, all 8 electrons that carbon gets for its octet is involved in bonding, but there's still 8, so we're good. All right. Okay. So this last example has to do with nitrogen, diatomic nitrogen. Okay, so if you look at the periodic table, I'm just going to say, okay, nitrogen is in group 5A, so it's going to need 3. We want 3 electrons. So each nitrogen needs 3 electrons. All right. So let's just draw the Lewis structure for each nitrogen and just see how it comes together. So nitrogen is helium. See, I tried to cheat and take a shortcut, but I still have to write the electron configuration anyway. Helium, 2s2, 2p3. Right, so let's write that out as a Lewis dot structure. And again, we would need to follow Hund's rule and make sure that everything is paired to resemble that of an electron diagram. So I'm going to put those first 2 s electrons in first and pair them. But then there's 3 p electrons, and they all go around nitrogen singly. Because if we drew it, it would look like that. So we want to draw this nitrogen with 3 lone electrons. And then we can do the same here with that one. So you can see each nitrogen needs 3 electrons. Each of these lonely neutral nitrogens have 3 single electrons, and each nitrogen needs 3 electrons. So very simply, what's going to happen is that each one of these lonely electrons is going to pair with the other lonely electron, and we are going to form a triple bond. Nitrogen 1, 2, 3, and then you can see all the electrons that aren't involved in bonding, so in this case, these electrons here, those will be lone pairs on nitrogen. Don't forget those. All right. And so triple bond nitrogen, nitrogen gas is a very inert gas. It doesn't react with anything for the most part. And the reason is because that triple bond is so strong, it is very hard to break. Because remember how we said that strength of bonds increases and gets shorter when you go from a bond order from 1 to 2 to 3. All right, and so again, let's check our work. There are 6 electrons total involved in bonding here. So if we want to ask ourselves, is nitrogen's octet fulfilled? So 2 plus 6 equals 8. Yes, fantastic. All right, so I kind of shown you in the last couple examples how I've drawn Lewis structures for full molecules. So I will now show you or give you the complete breakdown of the steps you go through when trying to draw a Lewis structure. So let me 4 molecules, 4 whole molecules. So don't confuse Lewis structures with Lewis dot structures. So maybe I'll just say different from Lewis dot. Kind of different. Sort of different. Sorta. So for Lewis dot, usually I'm talking about one atom. But for a whole Lewis structure, you're usually putting together multiple atoms to form a molecule. So sometimes when going through the steps to produce a Lewis structure, you might have to make a Lewis dot structure in order to arrive at the answer. All right, so the steps for drawing a Lewis structure. I will go through the steps, and then I think we'll just do some examples, and that's the best way to do it. But I've kind of already given you the skills and knowledge that you need to be able to do this. So the first step, probably the most important one, is first to determine the total number of valence electrons of all elements in the formula. All right, and again, this is for only the valence electrons. Yeah, so that's just what you do. So for our like CO2 example, so for CO2, carbon, I just look at my periodic table. Carbon it's in group 4, so 4 valence electrons. Oxygen has 6 valence electrons. It's in group 6A. So 6, but there's 2 oxygen, so that's times 2. So whatever, 16. So there's 16 electrons for CO2. All right, so that's just for example. So adjust for charge on the molecule or ion. So CO2 is a neutral molecule, so I don't have to do anything to my electron count. But let's say I'm just going to give a hypothetical compound. Let's say I was talking about CO2 minus, or let's do plus first. CO2 plus. So if there's a positive charge on the molecule, after you count up all the valence electrons, you want to subtract an electron. So we would, for CO2 plus, we would do 16 minus 1 equals 15, so 15 electrons. Or if this was CO2, these things actually don't exist, CO2 2 plus, we would subtract, in order to get a 2 plus charge, we need to remove 2 electrons. So you're going to do 16 minus 2 equals 14 electrons. All right, so that's if the molecule in question was a positive charge. Then if the overall charge of the molecule has a negative charge, so if we had CO2 minus, then you add an electron to the valence electron count. So maybe I should add that. To valence electron count in step 1. So CO2 minus, you want to do 16 plus 1 electron equals 17. Or if this was CO2 2 minus, it would be 16 plus 2 equals 18. So those are just a bunch of examples of how that would go. All right, so you know what atoms are in the molecule. You know how many valence electrons you need to put around all of the different atoms. So now the next thing to do is to draw a skeleton structure of the compound. So to draw a skeleton structure. So if it's diatomic, that's pretty easy. There's only one way you can really orient a diatomic, meaning two atoms. It doesn't matter which way you put it. But once you have like CO2, there's three atoms, and there's a lot of different arrangements that you could make. Like you could have it reading left to right. It could be like COO or OCO or like COO or OOC, whatever. There's a lot of different ways to do it. So just follow these rules that I have listed here. So typically, when in the formula, the central atom is usually written first, unless it's hydrogen is first. So for example, CO2, this how it's written C, this carbon will be the central atom, typically. So the formula typically gives the central atom away. So just like how we drew it before, carbon will be the center, so we know that the oxygens will flank the carbon on either side. And then to draw the skeleton structure, you just want to put a bond between everything. So now you've used up actually 2 of your electrons in our, how many electrons? 16 electron count. All right? Okay, so that's step 3. Then step 4 is to distribute electrons to the non-central atoms according to the octet rule. So we want to fulfill our octets now. Step 4 is to distribute electrons to the non-central atom according to the octet rule and electronegativity. So let's just redraw what I had up there. So we'll just do what it says. We'll distribute electrons to non-central atom according to octet rule. So this oxygen has 2 electrons right now. So we're going to do 1, 2, 3, 4, 5, 6, 7, 8. And do the same thing on this oxygen. 1, 2, 3, 4, 5, 6, 7, 8. So remember we needed 16 electrons, so we're done. So that's all there are 18 electrons in this picture right here. But this isn't our central atom, or sorry, this isn't our actual Lewis structure. So we have to go to the next step. So place remaining electrons on central atom. Well, we have no extra electrons. But look at this note here. If central atom is still electron deficient, meaning that there's less than 8 electrons, make multiple bonds to fulfill the octet. So that's what we're going to do. So this carbon only has 4 electrons. So if we move this electron pair here, this will add 2 electrons to carbon. And then also do the same thing here. So this carbon is deficient by 4 electrons. So this oxygen, how it's drawn, we're going to form a double bond, and then carbon can gain those extra 2 electrons that it needs twice to get 4 total. And so that's how we get our structure. So that lone pair is now becoming a bond. So we can rewrite CO2. So now there's a double bond to oxygen. It had 6 lone pairs, or sorry, had 3 lone pairs, and now it only has 2. So 1, 2, 1, 2, and the same thing on the other side. So this is actually the same CO2 structure that we talked about before. Right? And so some bonding exceptions. Hydrogen cannot make multiple bonds. It only ever needs 2 electrons to complete its valence shell. So you can also think that hydrogen will only make single bonds. Will only make single bonds. Which is kind of nice to know. So you never have to worry about multiple bonds when it comes to hydrogen. All right, and then the halogen group, or the group 7A, will also only form single bonds when they're the outer non-central atom. So that's kind of nice that they only form single bonds, so it's kind of simpler. You don't have to worry about multiple bonds. And so the only substances that we see multiple bonding occur, so CO2 was one of the examples where multiple bonding can occur, because that's always where it kind of gets hairy. So multiple bonding can occur with compounds that contain carbon, different color, carbon, nitrogen, and oxygen. So we already saw that CO2, right? Carbon can have multiple bonds. Nitrogen, we saw N2 has a triple bond on it, so nitrogen can form multiple bonding. And oxygen, again, oxygen in CO2, or actually O2 has, if you draw the Lewis structure for diatomic oxygen, there's actually a double bond. So all of these substances, carbons, nitrogen, oxygens, can have double bonds to it. And then finally, you can also see multiple bonds with sulfur when it's with a carbon, or a sulfur when it's with an oxygen. All right, so those are exceptions where we can have double bonds. So kind of just don't think about double bonds unless you see carbons, nitrogens, oxygens, or sulfur. We will see an example with multiple with one of these examples in the next coming slides, where we go through examples of different drawing Lewis structures.